Hello everyone. Today we will be presenting on the topic of logistic distribution. We will explore its history, key properties, real-world applications and how it is used in fields such as machine learning, statistics and economics. So, talking about the introduction of the logistic distribution, it is a simple yet powerful mathematical model used to describe a variety of processes, particularly those with binary outcomes or rapid growth and decay. One of its key characteristics is its S-shaped cumulative distribution function, which resembles a sigmoid curve. This shape makes it ideal for modeling probabilities where the outcome falls into one of two categories like yes or no or success and failure. Logistic distribution are often applied in different fields where probabilities need to be modeled, such as classification, problems in machine learning, or population growth in biology. Talking about the history and invention of the logistic distribution, it was first introduced in the 1830s by one of the Belgian mathematician. He was interested in modeling population growth under the constraint of limited resources. He realized that the initial growth of population often starts exponentially but slows down as the population nears its environmental capacity. His work laid the foundation for using logistic models in various fields such as biology, economics, and machine learning, where growth or probability models are needed. So, talking about the properties of the logistic distribution, one of the properties of logistic distribution is leptochotic. Logistic distribution has a sharper peak around the mean. That means more data is concentrated at the center as compared to other. For example, in a normal distribution, large amount of data is concentrated at the center. Another property is heavy tails. Logistic distribution has heavier tails. That means it accounts far more extreme values or outliers than the normal distribution. Parameters like alpha and beta are used for representation in the logistic distribution. Parameter alpha represents the location or mean of the distribution, whereas the parameter beta controls the spread or scale of the distribution. The logistic distribution forms the basis of logistic regression, which is one of the most widely used statistical techniques for binary classification. The mean of the logistic distribution is given by the location parameter alpha, while the standard deviation is calculated as given in the figure.
Okay, now let's talk about logistic regression. So, what it is? Uh, we are not gonna delve much deeper into this topic, but I'm gonna give you a surface idea of what it is. So, basically, a logistic regression is one of the most common applications of logistic distribution, or you can also say like logistic distribution is the mathematical foundation behind logistic regression. It is a statistical method used to model the probability of a binary outcome, essentially a yes or no decision. Logistic regression uses the logistic function or sigmoid curve to map a linear combination of inputs into a probability value between 0 and 1. Now, there are many many real world application across many domains of logistic regression, and I have put some of it here. First first is medical diagnosis. In medical diagnosis, uh, it helps it helps predict whether a patient is likely to have a certain disease based on the symptoms and medical history. And second is fraud detection. It is used to flag potential fraudulent transactions, such as those involving credit cards. And last one is spam detection. It is also another common application we see every day and each day in like when we use email. uh, Logistic regression is used in email to whether no it is a spam or not. So these are just a few regression examples that is based on logistic distribution that we use in our daily life, and there are many more applications that we use but we are unknown of that uses regression that is also based on logistic distribution. Okay, so why don't we move to key characteristics? There is not much to explain. It is some important mathematical characteristics of logistic distribution. I've just put some of it here. And the first one is PDF, also known as probability density function. It shows the likelihood of different outcomes for the logistic distribution, and it is expressed as the formula given below. The second one we know as CDF, also cumulative distribution function, gives the probability that a random variable is less or equal to a particular value, which is also represented by the below uh, formula. Here, mu is the location parameter determining the central point of the distribution, and s is the scale parameter controlling the spread. Obviously, the mean is also the mu, and the variance is also known as s square pi square upon 3, and it gives us an idea of how dispersed the data is. So after this, let's see what actually PDF and CDF is visually. So the logistic distribution probability density function is bell-shaped and symmetric, which is just like a normal distribution. However, the key difference here shows in CDF, that is cumulative distribution function, that is S-shaped, which is key to how it models probabilities. The PDF helps us understand the likelihood of the outcome across the distribution, while CDF gives us the cumulative probability up to a certain point. Together, these representations allow us to model real life probabilities and growth processes effectively. So moving on to understand how loss distribution is different to other distributions, I have picked up the most common distribution, normal distribution, to make you understand. Here, while the logistic and normal distribution look very similar, there are some key differences, and let's talk about it. I'm gonna explain the three most important, or let's say key differences that will give you the idea how normal distribution and logistic distribution is different. First one is shape. Both are symmetric, but the logistic distribution has heavier tails, which means it gives more weight to extreme values. And the next one is computation. The logistic distribution is computationally simpler because its CDF is a straightforward function, unlike the normal distribution, which requires more complex error function. And the third one and the last one is applications. The logistic distribution is used for modeling binary outcomes, such as in logistic regression, while the normal distribution is often used for continuous variables and hypothesis testing. So if you want to learn more about it, there is a table I have given in the slide. You can go through it briefly. Okay, so now this is what logistic distribution and normal distribution differences and similarities are. So we have now come up to our last slide. So wrapping up, the logistic distribution is an essential tool in modeling binary outcomes and processes with rapid growth or decay. Its versatility in real world applications such as logistic regression makes it a powerful tool in fields ranging from healthcare to finance. The characteristic S-shaped curve and its ability to handle extreme values make it uniquely suited for tasks that involve classification and decision making. Its simplicity and wide applicability ensures it remains a cornerstone of statistical analysis and machine learning.
Logistic regression is a statistical technique that models the probability and events given one or more independent variables. We will start with the input data that is of any numeric type, but the output variable will be binary. It will be 0 or 1, indicating a false or true value respectively. We then feed a curve called the logistic function to this data. It can then be used to make prediction of probability whether or not an event will happen, such as given so many hours of rain, what is the probability of a flood? Notice how that these points can project themselves onto the logistic function, and we can use maximum likelihood estimation to fit the curve, which we will talk about shortly. Notice there are these middle points where there is a mix of true and false cases. If these points follow a transitional trend of increasingly showing an event more likely to happen or not happen, we will see that S-shaped curve will climb or decrease respectively. We can then leverage it to predict probability between 0 and 1. Let's take a case where we expect 6.2 inches of rain and this is going to result in a 75% probability of a flood. If we divide a threshold, let's say 0.5, point 0.5, and anything greater than 0.5 point 0.5 will be true, anything less than 0.5 point 0.5 will be false. We will then predict there will be a flood. We can move this threshold based on our needs. For example, if we set it to 0.8, point 0.8, this will actually categorize as false and there won't be flood. We can also reduce it to say 0.2 point 0.2 and set a much lower variable to classifying a flood. This is the function that produces that curve. Here E is a Euler number, which is a special constant that beta 1 x plus beta 0 is a linear function. That is actually the log odd function. What is important to know is that this function will produce the S-shaped curve that we need to make prediction. We can also extend this to create more input variables and create multidimensional logistic regression as shown here. Let's talk about the estimation. The way it works is that we are going to take each of these points, multiply their corresponding likelihoods together, and that's going to produce our total likelihood. We need to find the beta coefficient that will maximize the likelihood of our S-shaped curve producing all of these points. This can be done with gradient descent, Newton's method, and other optimization techniques.